Welcome viewers to the fourth and the last segment of the eighth lecture for the online series of lectures for the course of linear algebra. Towards the end of the previous segment, we stated a theorem which relates the matrix representation of a linear operator on a finite dimensional vector space relative to two ordered bases B and B prime. Okay. So we found a relationship between these two objects um, by means of a theorem towards the end of the previous segment. We have seen that they are related by an invertible linear transformation P, where P inverse times um, these the matrix representation of this linear operator T relative to the basis B times P is equal to the matrix representation of the same linear operator T relative to the ordered basis B prime. So here B and B prime are ordered bases of the vector space V. Okay. All right, and we also studied its proof. Okay, the proof of theorem 4. So in this last segment, we are going to study an example uh, based on this, you know, based on the application of the theorem 4. Example 3. Let T be a linear operator defined by T x1 comma x2 is equal to x1 comma 0 as introduced in example 1. Okay, we studied this linear operator in example 1, and we also found its matrix representation relative to the canonical basis of F2. Okay, so T is the linear operator from on F2. Okay. In example 1, we have seen that the matrix representation of this guy T relative to the ordered basis B, where B is the standard basis comprising of these two vectors epsilon 1 being equal to 1 comma 0 and epsilon 2 being equal to 0 comma 1. And we have seen there that it can be represented by the following 2 times 2 matrix. Suppose B calligraphic B prime is the ordered basis for, we are choosing R2. Okay, is the ordered basis for R2 consisting of the vectors epsilon 1 prime equal to 1 comma 1 and epsilon 2 prime equal to 2 comma 1. It's easy to check that this P prime is actually a basis of R2. Okay. Then it is immediate that it is immediately found that epsilon 1 prime is equal to 1 times epsilon 1 plus 1 times epsilon 2, and epsilon 2 prime is going to be 2 times epsilon 1 plus 1 times epsilon 2. Okay, so we number this as 19, as equation number 19. All right, so now what is going to be the first column of the matrix P? P is going to be a 2 times 2 matrix, right? So according to what we have studied before, this row is going to be the first column of the matrix P. So P1 is nothing but the coordinate matrix of epsilon 1 prime in the basis calligraphic B, okay, which is nothing but 1 1, right? And the second column of the matrix P, denoted by P2, is going to be the coordinate matrix of epsilon 2 prime relative to the basis B, which is 2 1. Okay, so we know that P is equal to P1 comma P2. You know, it's just a notation which states that P can be written as a collection of column vectors, right? And this is going to be this matrix 1 1 2 1. That's the invertible matrix. Okay, now we need to find the inverse of this guy following the standard algorithm that we studied before in one of the lectures, probably in lecture 3 or lecture 4. In lecture 3, so this is the matrix that we are dealing with using our theorem of basis change. We know that it's an invertible matrix, so let's find its inverse. So we have this identity matrix written on its side, and now I have to make this guy the identity matrix by applying elementary row operations, and whatever we end up with on the right side is going to be the inverse of the matrix P according to the um, inversion algorithm. Okay, so we apply this operation, minus r1 plus r2 is equal to r2 prime, and that will make this guy 0 1 2, right? And this one is 0 and this one is minus 1. Okay, and these two, the first row stays the same. We're just changing the second row, so this is going to be minus 1 and this is going to be 1. Okay, so now I need to make this guy plus 1, and that can be done by multiplying the entire second row with minus 1. So minus r2 is equal to r2 prime is the corresponding elementary row operation. So the first row stays the same, 1 0, and this is going to be 0, this is going to be 1, this is going to be plus 1, this is going to be minus 1. Okay, so now the goal is to make this 0, and that can be done by the elementary row operation given by minus 2 r2 plus r1 is equal to r1 prime, right? That will make this guy 0, right? And this guy is going to be minus 2 multiplied with 1 is minus 2, and minus 2 added to plus 1 is minus 1, right? And then when I multiply this with 2, minus 2, it becomes a plus 2, and when I add this plus 2 with 0, I end up with 2. And the first row stays the same. So we produce an identity matrix on the left, and we are left with this 2 times 2 matrix on the right. That is going to be P inverse. Okay. So we have found P inverse using the standard inversion algorithm to be this 2 times 2 matrix, minus 1, 2, 1, minus 1. Okay, good. Now, according to Theorem 4 that we uh, proved in the previous segment, the uh, the matrix representation of this linear operator relative to this new basis B prime is equal to P inverse times the matrix representation of the same linear operator relative to the canonical basis B times the invertible matrix P. And this is going to be, we know that this is our P inverse that we found a while ago, and that gets multiplied with the matrix representation that we found in one of the previous segments, 1 0 0 0 in example 1. And then I have the invertible matrix P, which is 1 2 1 1. Let me check if I'm right. 1 2 1 1, that's correct. And the inverse, let me check, minus 1 2 1 minus 1, that's right. So now we do the matrix multiplication. This is minus 1 2 1 minus 1, and when I do this matrix multiplication, then I end up with 1 here, 2 here, 0 here, 0 here, and finally one has minus 1 here, minus 2 here, 1 here, and 2 here. Okay. Now we try to find this guy independently now and check if it matches with our result here. Try to find this thing independently. By independently, I mean that without the use of Theorem 4. Okay, and check that with this, cross match that with this result that we found using Theorem 4. Okay, so now remember that that the linear operator T from R2 on the vector space R2 was defined by this expression. Okay. Now, what was epsilon 1 prime? Remember epsilon 1 prime, the vector, the basis vector epsilon 1 prime in the basis B prime was 1 comma 1, and epsilon 2 prime was 2 comma 1. Okay. So now when epsilon 1 prime is acted upon by T, one obtains the following ordered pair. According to this formula, it's going to be 1 0, right? And now I'm going to express everything as a linear combination. Since R2 is the vector space and R2 has two bases, two ordered bases, two given ordered bases, B and B prime. So this guy is a vector in R2, and I'm going to express it as a linear combination of the basis vectors in this basis. No, I think no, we're not doing that. We are going to express it using the same basis B prime. So 1 comma 0 is a vector in R2, and we are going to express this vector using the using a linear combination of the vectors here in B prime. So let us write it as epsilon A times epsilon 1 prime plus B times epsilon 2 prime, okay, which is A times 1 comma 1 plus B times 2 comma 1. Okay, so do the same for the vector epsilon 2 prime. So have it acted upon by T, and that means that T is acting on this ordered pair, and according to this formula it's going to be 2 comma 0, and I write it as C times epsilon 1 prime plus D times epsilon 2 prime. I write this thing as a linear combination of the basis vectors in this basis B prime, and this is going to be C times 1 comma 1 plus D times 2 comma 1. Okay, so now we have a system of two linear equations, right? 1 comma 0 is equal to A plus 2B comma A plus B, right? And 2 comma 0 is C plus 2D and C plus D. So no, I think we have system of four linear equations in four unknowns. Okay, it's not just a system of two linear equations, sorry for that. So what we have is A plus 2B is equal to 1, then one has A plus B is equal to 0, then one has C plus 2D to be equal to 2, and then one has C plus D is equal to 0. Okay, so here we immediately see that D is equal to minus C. I plug it in here to have C plus 2 times minus C to be equal to 2, and that means that minus C is equal to 2, right? Implying C is equal to minus 2, and since C plus D is equal to 0, D is equal to 2. Okay, now we see from here that B is equal to minus A, and we have A minus 2A to be equal to 1, which means A is equal to minus 1. A is equal to minus 1 means B is equal to 1. Okay, hence T acting on epsilon 1 prime is equal to minus it's a times epsilon 1 prime plus b times epsilon 2 prime. So we are going to have minus epsilon 1 prime plus epsilon 2 prime. Okay, and T acting on epsilon 2 prime produces a vector which can be written as a linear combination of these two basis vectors for the order basis B prime, which reads as 2 times epsilon 1 prime, since C is equal to minus 2. Hence, this is minus 2 times epsilon 1 prime plus, we know D is 2, so this is 2 times epsilon 2 prime. Okay, so now we know that using results from previous segments, we know that the matrix representation of this linear operator relative to the ordered basis B prime is going to be minus 1, 1. This is going to be the first column, and minus 2, 2. Which agrees with what we found earlier using Theorem 4, right? So we have seen that, so we used this formula to find it earlier, and which was exactly the same matrix that we find here. Okay, so that was a verification of the result of Theorem 4 using using the definition of a linear operator on the vector space R2, R2 being a vector space over R. Okay, all right. Now I suggest a few exercises for you based on matrix representations of linear transformations. Page 95 of our textbook by Hoffman and Kunz. Problem number 1, 2, 5, 6, and 7. Okay. All right, so that's the end of the 8th lecture. Thank you for attending this 8th lecture.